Okay, we've done the first 6 questions, and we're going to skip the 7th one. So now we're going to go over to the 8th one. The reason we're skipping the 7th one is something you'll have to figure out yourself. Okay, so we're doing the 8th question. Let's copy paste it over to a new page. Okay, so as before, we're trying to prove whether or not this language over here is regular. If it's regular, we make a DFA NFA. If it's not regular, we use pump lemma. Let's first read this language. So it's all strings W, where W contains 4 times as many A's as B's. So for example, you could have A, 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 B. Or we could have A, B, A. There's 4 times as many A's as B's. And just as a reminder, the string is over the alphabet A, B. Okay, so that's what the language is like. So it's similar to one we did before. And so the proof is going to be very similar. This is not a regular language because you wouldn't be able to make a DFA for this. You'd need an infinite amount of states to keep track of the imbalance of A's and B's. So it's not regular. So let's copy paste the pumping lemma boilerplate. There we go. And let's proceed with the proof. So as before, we are looking for a string in the language with length greater than or equal to n that can lead us to some sort of contradiction. So by pumping it either up or down, we reach some sort of issue. So let's pick a string. So as before, when you're picking a string, think about the second property. If we set the first n characters of the string to be something like a single character, then x and y will only be able to contain that character. And by extension, y will have to have that character. So if we pump it up or down, we'll only be removing or adding that character. So let's pick a string where there's 4 times as many A's as B's and see where it gets us. So one example string would be B, N, A, 4N. So this string has 4 times as many A's as B's. Therefore, it is in the language. And the length of the string is 5n, which is greater or equal to n, as required by the pumping lemma. This tells us that there must exist a breakdown. Also, just to reiterate, the n over here is in reference to the pumping length that we mentioned in the boilerplate. So there must exist a breakdown. W equals to x, y, z, such that the 3 pumping lemma properties hold. There we go. Again, because the first n characters of the string are b's, and the length of x, y can only be at most n, x and y can only contain b's. So by property 2, x, y consists only of b's, no matter how you break it down. How w is broken down. And so because y is non-empty and xy as a whole contains only b's, y must contain at least one b. So by property 1, y contains at least one b. And what that tells us is that if we pump the string up or down, so we either remove y or repeat it any number of times, we'll be either removing or adding at least one b to the string. So by, let's just say we pump down. We get string. Oh, let's also give the amount of b's in y a name. So let's say that the amount of b's in y is k. Let k equal to the, so let k be the number of b's in y. So y equals to b to the k for some k greater than or equal to 1. So y has some amount of b's. So by pumping down, we get string we get string x, y, 0, z, which is equal to, so let's see what it's equal to. So before we had n b's, but we pumped down the string, so we removed y. Y had k v's, and so by pumping down, we have removed k b's from the start. So if we had n before, we now have n minus k. So we have n minus k b's, and we still have 4n a's, right? And what does this tell us? So for this string to be in the language, what we need is that there are 4 times as many a's as b's. So for there to be 4 times as many a's as b's, how many b's do we need? So we have 4n a's. The amount of b's we need is 4n divided by 4, which is just going to be n. So what we need is to have n b's, but we have n minus k b's. And because k must be greater than or equal to 1, so k can't be 0, n minus k cannot equal to n. And so there's no way that this string has 4 times as many a's as b's. So for x, y, 0, z to be in the language, to be in L, we must have that it contains n b's, but x, y, 0, z contains n minus k b's, which is not equal to n. Because n minus k, because k is greater than or equal to 1. So in other words, k is not equal to 0. So we have n minus k b's. For this to be equal to n, so for this to be equal to n, we must have that k equals to 0. But k cannot be 0 because it's greater than or equal to n. So therefore, we know that it's not equal to n. So therefore, x, y, 0, z is not in the language because we don't have 4 times as many a's as b's. This contradicts property 3. Property 3 of the pumping lemma. So by property 3, we need to have that x, y, 0, z is in the language. But we didn't have it, so it's a contradiction. So by contradiction, L could not have been regular, so L is not regular. And that's the end of the proof. Okay, on to the next one.